Now, what happens when the system is superheated? That is, as opposed to accepting saturated vapor at the inlet of our turbine, we are going to superheat the fluid before it enters our turbine. Thus, state 3 is going to move from our saturated vapor curve into our superheated vapor, and state 4 is going to correspondingly move on our x-axis, i.e. the entropy is going to increase as well as the quality. Now, let's assume that steam enters our turbine at 8 MPa in a temperature of 480 degrees centigrade, and that saturated liquid exits the condenser at 8 kPa. If the net power produced is 100 megawatts, we want to determine the thermal efficiency, the backwork ratio, the mass flow rate of the steam, the rate of heat supplied to the boiler, and the rate of heat rejected from the condenser. To begin, we'll list our state variables, and we recognize that the enthalpy values of state 1 and state 2 remain the same. For the performance of our condenser, i.e. the exit value in terms of pressure and quality, and the exit of our pump, i.e. pressure, have not changed. Thus, we need to determine our enthalpy at state 3 and state 4 before we reevaluate our expressions. Our enthalpy at state 3 is found from our superheated vapor tables. That is, our enthalpy at state 3, given our pressure of 8,000 kPa, a temperature of 480 degrees centigrade, is found as 3,347.758 kilojoule per kg. Our entropy at state 3 is also found from our superheated vapor tables, such that S3 is equal to 6.65634 kilojoule per kg. Now we can determine our enthalpy at state 4 as we did in example 1, relating our entropy and enthalpy values. Our enthalpy value is equal to S4 minus SF per SG minus FF times the quantity Hg minus HF plus HF. Or our enthalpy at state 4 is 2081.272 kilojoule per kg. Thus, our thermal efficiency is evaluated as H3 less H4 minus H2 less H1 per H3 minus H2. Our thermal efficiency for the superheated cycle, once we substitute in our respective enthalpy values, is found to be 39.7%. This efficiency has increased in comparison to our Rankine cycle in example 1. If we calculate our backwork ratio, i.e. H2 less H1 per H3 less H4, we find our backwork ratio is 6.36 e to the minus 3. Our backwork ratio has also decreased, i.e. the work of our turbine has increased since our pump work has remained the same. To calculate the mass flow rate of the steam, we're going to relate our net power to our turbine work and our pump work. Our mass flow rate of our steam times the quantity H3 less H4 minus the quantity H2 less H1 has to be equal to 100 megawatts. Substituting in our updated enthalpy values at state 3 and state 4, we find that the mass flow rate of our steam is 79.44 kilograms per second. This value has decreased in comparison to the mass flow rate of the steam in example 1. When we calculate the heat supplied to our boiler, we have m dot H3 less H2. Although our final temperature at state 3 has increased, and thus our enthalpy has increased, our mass flow rate has drastically decreased. We see that our heat supplied to our boiler, once we substitute in our enthalpy values, is 251.53 megawatts. This value has decreased in comparison to our previous Rankine cycle. Last but not least, the heat rejected from our condenser, m dot H4 less H1, although H4 has increased because the quality of our fluid has increased as it's rejected from our turbine, our mass flow rate has decreased in a greater amount. Thus, when we substitute in our enthalpy values, we find that the heat rejected from our condenser is 151.56 megawatts. This value has also decreased in comparison to the Rankine cycle in example 1. We can conclude that superheating allows us to achieve a higher efficiency. That is, we are increasing the temperature of our hot side temperature reservoir.